Day everybody. So just now we have done with Western Bridge. So now what I'm going to do is meter bridge. We are going to apply the principle of Western Bridge to understand meter bridge and potentiometer. So this time what I'm going to do is I'm going to do with meter bridge and potentiometers. All right. Now the purpose of understanding or purpose of doing meter bridge is to find out unknown resistance. All right. So this is the diagram, or this is the picture of meter bridge. So meter bridge looks like this. All right. So it consists of, look at here, this is the board, and this has 1 meter resistant wire is fixed at 2 ends. All right. And then we are having a 2 gate where I'm going to put resistance, right? One resistance is going to be an unknown, other resistance is going to be a standard, that is non-resistance. Now this is a metal strip. Normally we use a copper metal strips. All right. Why we use a copper metal strip? Copper is very good conductors. The resistance is almost 0. So what we are going to use is, here you will be having a resistance, here you will be having a resistance, no resistance all along, and this is all resistance. Why? Because I'm going to use resistant wire, nickel wire normally, right? So this is what I have, right? So metal strips, 2 gate, where I'm going to provide, where I'm going to fix, this is unknown. This is unknown resistance. This could be unknown. This would be known. That is a standard resistance. And this is all resistant, right? So I'm going to achieve a balanced conditions. Okay. So this is the diagram of Western Bridge. This is the diagram of Western Bridge. Not Western. I'm sorry. This is meter bridge. So this is here I have kept 1 meter. Scales in order to understand the length of a wire, right? Okay, this is what I have, and now this is how I'm going to do, right? Now this is the board which I told you, and this is unknown resistance. Here I'm going to put an unknown resistance, and then this is a jockey. This is a jockey which I have written here. This is a jockey. The job of jockey is to run, slide. I just slide jockey over a resistant wire. This is a resistant wire, right? I just sliding, right? A jockey over a resistant wire, and this is a standard resistance box. This is a standard resistance box. If I remove a 2, it is going to be a 2 ohm. If I remove a 3, this is going to be a 3 ohm. Alright. And this is a galvanometer. The galvanometer, the job of galvanometer is to check whether there is a current or not. So our job is to reduce the current to 0. So I'm going to change. I'll give this and slide and fix at a point where you get 0 current. Where you get 0 current. So this is P. This is the battery I supply. So look at here. If I fix a resistant, unknown resistant here, if I fix the unknown resistant here, and then now this is something like this, right? I have a resistant like this, I have resistant like this, then I have resistant all along like this, and the jockey. This is a galvanometer. The jockey which I am going to provide will divide this 1 meter resistant wire into a 2 part. 1 meter wire into a 2 part. All right, 1 meter wire into a 2 part. Now this is going to be a 1 resistant number. Let's say this is resistant number 3. This is resistant number 2. This is resistant number 4, and this is the shape of Western Bridge. This is the shape of Western Bridge. All right. So this is what I have here, right? So look at here. Now This is the diagram, right? All right. Now what I'm going to do is, look at here. This is unknown resistance, right? This wire, I told you this is a wire of 100 centimeter or 1 meters. This is a wire of 100 centimeters. The resistance is unknown. Resistance is unknown. Let me draw here. Like this is a wire. Let's say this is A. This is B. Let's say we got some resistance. Let's say resistance R prime. This is some resistance R prime, right? So we won't know the resistance of this wire of length 1 meters. However, what we try to understand is, since this wire, resistance wire thickness is uniforms, this wire thickness is uniforms. All right. So resistance per centimeter, resistance per length. Let's say resistance per length remain constants. Why it remain constant? Since the thickness is uniforms, now as you increase the length, resistance is going to increase. So resistance is proportional to length. Therefore, resistance per length. Alright, therefore I am going to write resistance per length is constant. Resistance per length is constants for a given wire, given resistance wire. Alright, so therefore I write here, this is what we have written. Resistance per centimeter is going to be RL divided by L. So therefore RL is equal to resistance per centimeter into L. So resistance per centimeter is fixed for a given wire. Alright. And then we can easily find out resistance, right? If let's say what is the resistance for length L? Resistance for length L is going to be this much. This is a resistance for length L. This is a resistance for length L. Or resistance per centimeter multiplied by length is going to become resistance per centimeter multiplied by L is resistance for length L. So that you should keep in mind. Very, very important concept. So having this concept, now I say that this is a standard non-resistance. This is a standard non-resistance where you put a resistance box, which I have drawn in the diagram, and this is unknown resistance. All right. So now what I'm going to do is, I'm going to slide a jockey. Look at here. If I put a jockey here. Galvanometer moves in one direction. Why? Because this is not balanced. If I keep a jockey at that side, this will go in opposite direction. Why? Because this is more at that side, this is more at that side, right? R by very small is not equal to S by big. Alright, so therefore it is not balanced. It is not balanced. Now what I'm going to do is I just move this jockey and such that if galvanometer marks 0, if a galvanometer goes to 0, once the galvanometer goes to 0, let's say, so at L is equal to L1s, if L is equal to L1s, then IG becomes zeros. IG becomes 0 means now this is at balance condition. That this implies, which implies it is at balance. It is at balance point. It is at balance point. If it is at balance point, now we have done this in the Whiston bridge. The ratio of these two is, the ratio of this side is equal to that side. So what is the ratio of this side? So this resistance is going to be RCML. I'm going to say up to this resistance is going to be this. Up to that resistance is going to be RCM 100 minus L. Why 100? It is this is of a length 100 centimeters. So 100 minus L is going to be this length. Alright, so therefore I just say R divided by RCML. Alright, RCML, this ratio. Alright, then S divided by RCM 100 minus L. So this is the balance condition. This is the restored bridge concept. So once I get this, R is equal to S RCML divided by RCM 100 minus L. So these two cancel out. So finally I get this is equal to SL divided by 100 minus L. So this is the answer. This is unknown resistance. This is how you are going to get it. This is how you are going to get unknown resistance. Unknown resistance, right? So we use the resistance per centimeter concept to find out resistance of a wire. Resistance of a 100 centimeter wire. But this is not necessary. Why? Because these two cancel out. Why? Because these two are same, right? For a particular wire, RCM remains same. So these two cancel out. Finally, you get this. Finally, you get this. Alright, so this is for meter bridge. This is for meter bridge. So this will help us to find out R. This will help us to find out R. This will help us to find out R. And look at here, one more information, right? Very important is, if I use a different S, the balance point also is going to change. Balance point also is going to change. Alright, balance point. Why? Because so that the ratio should remain same. These two ratios should remain these two ratios, right? Or else I just write R divided by S ratio should be equal to L divided by L1 divided by 100 minus L1 ratio. That should be it, right? Say if I say if these two are equal, if these two are equal, if these two are equal, then this is going to become 1. Alright, this is going to become 1. When L1 is going to become, if L1 is equal to 50, if it is a 50, then 100 minus 50 is 50, cancel out 1. So this is what I have. So if R and S are equal, right? If R is equal to S, then the balance point must be equal to 50 centimeters. That's the point, right? So now look at here. Now I'll do some small kind of exercise. Let's say if R2 is, let's say, if R2 is, let's say 2 ohm, all right, and then R3 is, let's say, this S is 4 ohms, and what is the null point ratio, right? So null point ratio I really don't know, and I find out, and how to find out is 200 minus 2L1 equal to 4L1. Okay, this goes this side. So how much? 200 equal to 6L1. And L1 is equal to divided by 6, and 6 3s are 18, 6 3s are 18, and 6 3s are 18, 33.33 centimeters. So this is how you are going to get it. This, if I say if R1 is 2 and R is 2 and RS is 4. Now if I say, look, you should see it so that in exam, if I increase the R where the null point is, if I decrease the R where the null point is, you can easily able to answer, right? Now if I say if R is equal to, let's say if R is equal to 4 ohm, R is greater, right? And then if S is equal to 2 ohm, and where would be a null point, right? So therefore I just say this is 4 divided by 2 equal to L1 divided by 100 minus L1. So this is equal to 400 minus 4L1 equal to 2L1. Alright. And then minus L1, 400. Yes. So therefore, how much are we going to get it? This 400 equal to 600 L1. Where would be same, right? L1. I'll do like this. Look at here. 200, this goes this side. 400, 6, right? This is 6. Alright. So now this is equal to 2 equal to L1 divided by 100 minus L. 200 minus L equal to L. 200 equal to 2L. And then I'm sorry, this is 2L and this is 3L, and L is equal to 6 and 6.66 centimeters. So this is L1, value of L1. I'm talking about value of L1. So conclusion here is, if I increase this R, then the null point goes this side. This is my conclusion, right? This is the reason why I do this, is to know you, to just let you know that if R1 increases, then null point goes this side. If this side increases, if this side increases, the null point goes in this side. And if S increases, and null point goes that side. If these two are equal, then null point stays exactly at halfway. So again I am repeating. Alright. So this helps us to understand that if R increases, null point moves toward C. Alright. And if right here, right? If R is greater than S, then null point moves towards C. Alright. And then if S is more than R, then null point moves toward A. And then finally I say if R is equal to S, then null point is at midway on the point. So this is what you should know at least. Alright. So this is what I have meter bridge. So as I have written something like this, meter bridge explanations are done, right? So meter bridge consists of 1 meter, a wire of 1 meter length and uniform cross-section area stretched and top and climbed between two thick metallic strips bent at the right angles. Metallic strip has a 2 gate across which resistor can be connected. A, B are connected to cells. Alright, these things are done, right? So this is what meter bridge is all about. So the objective of studying meter bridge is to find out unknown resistance. Alright? To find out unknown resistance. So this is what I have. Now, if I put this parallel, right? If I put this parallel, then this side is going to decrease. If this side is going to decrease, then the null point has to move this side. If I put here a series combination, this is I have done, right? This is one problem. Another problem is, I just made this like this. If I do that, this goes along this side. Why? Because resistance is going to decrease. If I put a resistance series with S, then this becomes higher and this goes this side. Alright. This you can do as a home assignment, right? Now what I'm going to do is potentiometers. Alright. The last topic of this chapter, very important for exam as well as practical, right? We should understand what this is a potentiometer board. This is a potentiometer board. So potentiometer is a device very similar to this looks like a meter bridge. Only difference is that potentiometer has a series of wires. Here in this case 1, 2, 3, 4, 5, 6, so many wires. In our lab we will be having a wire of 4 length. 1, 2, 3, 4. This wire, right? We will be having in our lab. We will be having 1 wire, 2 wire, 3rd wire, 4th wire up to this. So this is the 2 terminals. Alright. So you will have a different wires, right? 3, 4 sets of wire, each having a length 1 meters. 1 meter is equivalent to 100 centimeters. Alright. Then you have this is ammeter. Alright. This is a battery. Primary source battery, and this is milliammeters. This is resistance box. This is called a rheostat. This is called a rheostat, right? This is called a rheostat. Rheostat is normally what we call as variable resistance, right? So this is key. This is called a 2-way key. This is a 1-way key. So these are the circuit components which you are going to come across in a lab, right? So just for your understanding, I have shown this, right? This is the potentiometer board logo, right? Now look at here. So the purpose of potentiometer here is, or the objective of studying potentiometer is 2 things. One is to compare EMF, or to find out unknown EMF having a non-EMF, alright, that is a standard EMF, and the second objective is to find out internal resistance. And one very important, frequently come in exams, using a voltmeter, we won't be able to measure EMF of a cell, alright. Reason is that when I put a voltmeter, there will be a current. So if there is a current, then internal resistance come into play, and then we won't be able to find out. So this device help us to find out EMF of a cell. Why? Because we just do this right under null condition, null point condition. Null point condition means where there is no current, right? So therefore, when there is no current, then internal resistance doesn't appears, and then we would able to find out EMF correctly, right? So how we are going to find out EMF? You will see it here, right? So this is the diagram, right? This is again diagram. This is called a jockey, which I have shown you, right? And this is exactly our lab potentiometer. Like why? Because 1, 2, 3, 4 wire potentiometer. All right. This is a 1 meter length meter scale. All right. So this looks a little complicated, but when you do this in a lab, this is very simple, right? This is milliammeter. Why we need milliammeter is to maintain a current so that voltage doesn't change, potential across the wire doesn't change, right? That's you'll understand better in the lab, right? This is a galvanometer. This is a high resistance box. This is a high resistance box, and this is a shunt resistance, a small resistance. This is a key, and this is a rheostat. This is a rheostat. And this is a diagram. Just for your understanding, I have shown this diagram. Now I'm going to start from here, right? This is what we call as a primary circuit. This is what we call as a primary circuit. Again, I'll write here also. Here are so many wires, right? So I will put here a 4 wire potentiometer, right? Wire potentiometer. This is metal state. This is a 4-wire potentiometer. Alright. And then I'm going to connect this to a primary cell. This is what we call as a driver cell. This is what we call as a driver cell. And this is connected to a rheostat. Here we haven't done. Normally we will put this in the rheostat. The purpose of connecting a rheostat is to change a current in a potentiometer circuit, right? So this once I introduce, there will be a current, and this is what we call as a steady current. This is what we call as a steady current. And this current I can vary by changing a rheostat. If I change a rheostat, and the current in a wire is going to change. Current in a wire is going to change. And you ask me, what is the significance of this current in a wire, right? So the significance is that since there is a current remains same throughout the wires, there will be a potential drop or potential across a wire. There will be a potential drop across a wire, right? So this is what we have. And again, since the wires are uniform, the potential increase is uniform, right? I go on uniformly increases along length. Potential increases uniformly along a length. Again, I am repeating, potential increases uniformly along a length. Alright, since the potential increases uniformly along a length, then I say the potential is proportional to length, and then L. This is what we call as potential per unit length, or this is what we call as potential gradients. This is what we call as potential gradients. So that means potential gradient remains same unless we change current. How are we going to change a current? Moving a rheostat. So therefore we used to fix the rheostat, and therefore we normally put here milliampere. So if an ampere doesn't change, if a value of milliampere doesn't change, then we say that the current in a steady current remains same. Steady current doesn't change, right? So this is very, very. This is what we call as a primary circuit. So primary circuit has what? Steady currents, and primary circuit we talk about potential gradients, and potential along a wire changes, increases uniformly along a wire. So therefore V is equal to phi L. Where phi is what we call as potential gradients. This is one very, very important. Now once we get this, now what I'm going to do is I'm going to compare EMF, or I'm going to find out unknown resistance using standard resistance, right? So this is the circuit I have. Alright, so initially what I'm doing now, this is fixed. There will be this has a potential gradients of phi is a potential gradients along these wires. And now what I'm going to do is, the first thing what I'm going to do is I just close this, and this remain open, and this is, I close the key joint 1 and 3, joint 1 and 3. If I join 1 and 3, I'm going to get E1. So now look at here. This is a potential which is going to balance this. So therefore, positive of this cell is connected to the positive of primary cell. So this is what we call as a secondary cells. Alright, this is what we call as a secondary cell. Alright, so and so this cell is going to balance with these potentials. If cell is greater, then the potential is going to be this is going to balance with greater potential. If cell having a smaller EMF, then for we achieve a balance at a smaller potential. That's the simple concept, right? That is the balance concept. So if let's say I'll give you an example, right? I'm having a balance. I'm having a balance. Let's say if I have a 2 kg here, all right. If I have a 2 kg here, then how to measure this? How to measure 2 kg here, right? How to measure that it is 2 kg, right? I go on putting a standard weighing mass, and once you get a 2 kg, and these two are balanced. These two are balanced, right? So now if it is a 3 kg, then I have to put more. If it is a 4 kg, I have to put more, right? So this is something like potential across AC. This is something like potential across AC. All right. So every time I change this according with this. This is fixed, right? And this is EMF of secondary cell. This is analogy I'm giving, right? This is the analogy I'm giving. All right. So look at here. If I have no weighing mass, if this mass is more than this weighing mass, all right, then you won't be able to achieve balance. You won't be able to achieve a balance. Why? Because this is going to be more, and I have no more mass to aid. So therefore, we can achieve a balance, right? So this is again I'm going to come here, right? So let's say join 1 and 3. If I join 1 and 3, and now this is going to balance with this. So this is fixed. I just run, and I say somehow I get balance at this point. So that balance at that point means it says that E1 is equal to let's say how much is that length, right? So phi L1. All right. I got a balance at L1. So what is the potential? Potential is equal to phi L1. This is equation number 1. Now next I remove this and join 2, 3, like join 2 and 3. So now this is a different cell, and I would get a different balance point, right? So somehow I got a balance point here. That means this EMF is more than that EMF. So you need a longer length, right? So again I say that we achieve a balance at this. Alright, so phi means L is shorter here, L is longer here, right? This is equation number 2. Now I compare these two equations. I compare equation 1 and equation 2, right? Compare 1 and 2. If I compare 1 and 2, this is going to get yes, this is what I found. So L2 has to be a longer. Why? Because E2 is greater. So this is how I balance, right? This is how I compare, right? If a ratio is more than 1, then E1 is greater. If this ratio is less than 1, then E2 is greater. So this is how I compare EMF. This is how I compare EMF. Now let's say if EMF2 is standard EMF, right? EMF2 is known. Let's say it is known. Then EMF1 is unknown. Then this can be found. Yes. Yeah. This is how you're going to find. How you're going to find out. This is EMF 1. Alright. So the galvanometer is very essential. Why? Because where to get balance point is given by the galvanometer goes to 0, then we achieve that this balance point. So this is very, very important. So this is how we are going to get it. We are going to get unknown EMF, or we are going to compare EMF. So this is the first part. This is the first part. Now look at here. If I say if this potential, right, let's say if this EMF 2 is more than cell of driver cell, let's say A, then this implies that this is going to be more than potential from A to C, potential from A to C. If this is so, then we won't get balance point. We won't get balance point. Why? Because even if I reach here, alright, still you need more wire, more potential to be balanced, right? So this is very, very important. This may appear like this. This is same like this. If varying mass is less than what you are going to measure, what you are going to rate, then you won't be able to find out. Alright, that's the one very important, right? This is how we are going to compare EMF. So now next what I'm going to do is how to find out internal resistance. How to find out internal resistance. This is what I have done it. So this is for internal resistance. Again, this remains same. This remains same. That is why I didn't love this, right? This remains same. Now once you get this, now we are going to get for internal resistance. So this is the resistance box. This is what we call as shunt resistance. Shunt resistance. Shunt resistance means a small resistance. This is the small resistance, right? So to find out unknown internal resistance, what we are going to do is, look at here, as this remains same. First, I achieve these conditions. All right. I just allow us the fixed current to pass through it, and I will get resistance pass. What is that? Potential gradients. And once we get a potential gradients, we can easily find out a potential all anomal length. Potential all anomal length. So now what I'm going to do is, first I open this circuit. This is not closed. This is open. So this is open, right? Key 2 is open. Key 2 is open. All right. Key 2 is open. And then what I say, if key 2 is open, this also play a role. So the balance point is at N2. Balance point at N1. Balance point is at N1. So therefore, E is equal to phi N1. So whatever EMF is, EMF E somehow balanced at this length. Alright, this is 1. Now what I did is I close this key. Key 2 is now closed. Key 2 is closed now. Once the key 2 is closed, alright, there will be a current. Right? There will be a current like this. There will be a current like this. Alright, and therefore we are going to find out resistance, potential like this. I'm going to write this is potential. This is the potentials. Once the key 2 is closed, then potential across cell is going to be a potential, right? EMF, right? cell is going to be our potential V. Once the Q2 is closed, then V is equal to, let's say, somehow I got at null point at L2. Now look at here, L2 is going to be less than L1. The reason is that potential is less than EMF. Potential is less than EMF, that we know, right? So this is equation number 2. Alright, once we get this, then I compare two equations. Compare 1 and 2. Once I compare 1 and 2, so therefore EMF divided by V is equal to phi L1 by phi L2. Cancel out. This is what we got. Alright, so I say that L1 must be, here I'm going to write, L1 must be more than L2. Why? Because one is EMF, one tells me about EMF, other tells me about potential, right? So now what I'm going to do is, what I'm going to do is, what is EMF? EMF is equal to V minus or plus I small r. So what is V? V is equal to IR plus I small r. Alright. So therefore V is equal to IR. Okay. So therefore I substitute here IR plus small r divided by IR is going to be L1 divided by L2. So LL cancel out, II cancel out. So R plus R is equal to L1 by L2. 1 plus small r divided by capital R is equal to 1 by R, R2. So R goes this side, R goes this side. R goes this side, 1 goes this side. So therefore I just say R is equal to L1 divided by L2 minus 1, and then R is equal to R L1 minus L2 divided by L. Yes, this is how we are going to find out internal resistance. So this is how we are going to find out internal resistance. This is how we are going to find. So anyway, I told you R L1 is more than L2. Alright, so therefore this is how we find out internal resistance. And alright. So with this we somehow could able to find out EMF, unknown EMF, compare EMF and internal resistance. Alright. So at last I will show you some diagram just to help you to understand or visualize, since otherwise in class I can show you whole electrical circuit, right? This is what I have. Okay, the better diagram is this. This is the diagram, right? So this is the diagram, alright, and how you are going to use it to determine the internal resistance of primary cell using a potentiometer. So that's the point. So with this, I have done with the third chapter, that is current electricity. So you do this exercise, right? You do this. You try to find out this answer. I've written 2 ohm, alright? And this again, this is same like this, alright? This will be having activity, right? So as I go on increasing, potential is going to increase, and the maximum potential is going to be this. Maximum potential is, so unknown potential difference, unknown potential, right? As I increase the length, potential is going to increase. If I put here, potential is going to become 0. Why? Length is 0, and this is going to be a maximum, right? And this maximum is almost equal to this if internal resistance is 0. Alright, so this potential is equal to that potential if internal resistance is 0. Alright, so with this I will stop here, and now next class I'm going to start in 4th chapter. Alright, so maybe if time permit we'll do a few problems. Thank you.